Well, hello, I'm Martin Green from UNSW Sydney, and today I'd like to talk to you about solar photovoltaics and how it's likely to be the power source for the future. I'm speaking to you from Sydney, and down the lower left there is the iconic Sydney Opera House, and in the middle is our laboratories at Sydney, and at the right is our solar industrial research facility. Looked like my two slides got a bit confused there. So the first bit of the talk, I'd like to talk about introduction. So, what I'll talk about is, how solar cells work and just what's been happening that makes their progress so outstanding over recent years. So this is a basic solar cell, and it's made from a semiconductor silicon. And silicon and all semiconductors have this particular property whereby internally there's a band of states that are not allowed to electrons within the material. So when you shine light onto the material, and light in its interaction with matter, Einstein showed it acts as if it was little particles. So when these particles, the photons, enter into the semiconductor material, if they have enough energy, they can excite an electron from lower energies within the material to higher energies across this band of states that are forbidden. So what that does is it holds the electron in that excited state much longer than would happen in a metal, because to drop back to its original state, it's got to give up this, fairly large packet of energy as far as an electron's concerned, and that takes some time for conditions to be right to do that. So in a metal, the electron would just quickly relax back. So that's why a semiconductor is important for solar. You hold the carriers in the excited state. You've got to do more than that, though. You've got to get them moving off in the right direction. So the electron is in the excited state and it leaves a vacant state behind, which acts as if it's a positive charge carrier. Other electrons can move into that vacant state, which, like a bubble, it looks like the vacant state is moving. So you design a solar cell with what's called a p-n junction in it, and you do that by adding dopants to the silicon. But the N-type dopants are the material, they make the material attractive to electrons. So electrons can move through that easily, and the P-type material, positive is what the P stands for, the holes can move easily through that. So you get the electrons going in one direction and the holes going in the other. And if you connect a contact between that are contacting the N and the P regions, and the electrons can flow around through that contact and meet up with the holes at the other side of the device, and everything works out. So you convert a photon in sunlight ideally into an electron that flows through the load. So it's just a quantum converter, photon in, electron out. The voltage that you can get out from it has to be lower than the band gap energy if you express that in electron volts. So a semiconductor typically has a band gap of about 1 electron volt, so the voltage output has to be less than 1 volt. So the solar cells need to be packaged to protect them from the environment, both mechanical impact and chemical corrosion and so on. So they're encapsulated quite neatly, and you can see some photos of modules on the left there. So the cells in those photos are square, and we'll see that dates them. But the drawing on the right shows how they're encapsulated. So generally under glass, because that's a cheap, transparent material and that's quite strong. And the glass is tempered to make it even stronger and less resistant to breaking, and able to withstand hailstones and that kind of thing. But you actually laminate the cells within that by using some transparent, soft polymeric material that when you press all the layers together and heat them, everything sort of melds together and you get this nice tightly packaged module, it's called. Because the cells, as I said, have quite a low voltage, less than 1 volt, they can generate quite a large amount of current. There's a lot of photons in sunlight. So the currents can be quite high. So a cell the size here, maybe 6-inch square, would generate about 10 amps, each cell. So, and that's a large amount of current to be able to handle. You need a lot of copper to handle that without resistive losses. So the cells are generally connected in series. So generally 60 or 72 in a package as shown here. So the voltage builds up and the current stays at that 10 amp value. These are more modern modules, and you'll notice the cells are rectangular, and I'll explain why that is a little bit later on. But the modules are getting bigger. So the man shown there is 6 foot tall. So you can see modules are getting big. You used to be able to tuck them under your arm, but now require 2 people to carry them. So at the lower right there, you can see ones that are actually 8 foot by 4 foot something or other. So getting really quite large. What's been happening with photovoltaics is the amount being installed has been growing quite rapidly. So this graph here shows both the accumulated amount of photovoltaics installed, which is now 760 gigawatts, or at least it was the end of 2020. So 1 gigawatt is about the size of a large coal or nuclear power station. So there's equivalent of 760 of those installed in the form of solar various places around the world. And the browner regions towards the top of those just show the annual installation of solar. And, both have been growing quickly, the total amount and the annual installation. So this graph here shows the same information in a slightly different way. It's a semi-logarithmic graph, and it's showing the annual installations, the brown bits in the previous graph. And last year there was something like 140 gigawatts of photovoltaics installed annually worldwide. So that's equivalent to 140 nuclear or coal-fired plant. And that's still growing quickly. So on this graph, a straight line, it represents exponential growth. So that's been growing exponentially over different segments that you can see there. But what's expected to happen over this coming decade is the industry is expected to grow towards this 1 terawatt a year level. So you can see 2 projections there. Well, the blue one is an optimistic one, and the red one is one that a market forecasting company has made, which is a little bit more conservative, but both showing approximately that 1 terawatt by the end of this decade. And that terawatt is quite important for reasons shown here. So this is a graph of global CO2 emissions up to 2014 in actuality, and then it shows it peaking around about now and 2021, and then one of these graphs showing the type of trajectory that you'd require, in this case to maintain global temperature rise to below 2 degrees centigrade. So the 1.5 degrees looking quite challenging now, but 2 degrees is more feasible. But it shows the problem we're facing in that the coloured regions at the bottom show the likely emissions from the 4 biggest emitters, taking into account their best efforts to reduce their own emissions. So you can see that there's a real problem looming towards the end of the decade in that these 4 biggest emitters alone are going to use up the whole budget for global CO2 emissions, with nothing left for the 200 or so extra other countries that aren't included there. But if you can reach this 1 terawatt of photovoltaics, the little arrows up the upper right there just show the impact of that in reducing CO2 emissions if it's displacing coal from electricity generation or oil from transport, which turn out to be 2 of the easier ones where solar can displace those 2 fossil fuels. So there's hope in that if we can get up to this terawatt a year level with photovoltaics quickly, we might be able to set ourselves on the right type of trajectory if we can install 1 terawatt year after year to maintain the type of slope that's shown in this scenario, maintaining reasonable temperature rise. So that's the hope. And the reason that the hope is increasing, that's going to be feasible, is the costs of photovoltaics has reduced quite dramatically, particularly over the last 10, 15 years. So this graph shows the progress over that type of period. And back in 2008, the modules were actually selling at the wholesale level for $4 a watt. So those modules on the right are about 300 watts. So it would have cost you, about $1,200 US for one of those in 2008. But now the price of those modules, at least at the wholesale level in volume, is 20 cents a watt. So a module of that type of rating would now cost $60. So a massive reduction in cost over that period. So 24 times in 12 or 13 years, is what we've seen. And that's, that's the reason that the uptake is growing exponentially and so on. These cost reductions are driving that uptake. This is just the same information shown on a logarithmic plot, and over recent years, with the different technologies, about 20% a year cost reduction is what we're seeing. It looks a little bit flat in the previous region, the more recent periods, but it's still reducing quite quickly. So that's the cost of the modules themselves. To use them, you've got to install them in a system, and the prices of electricity that are generated from installed systems are reducing rapidly as well. So this just shows recent experience with what are known as power purchase agreements. So many countries and cities contract for the supply of electricity through these power purchase agreements, and people with different technology can bid for supplying electricity, generally for 15 or 20 years is the type of period involved. And this graph here just shows the lowest bids in different parts of the world over the last 7 or 8 years. So we've seen the bids price come down very quickly as the cost of the modules themselves have reduced, and people have got more experienced with building these systems and building them bigger and so on. But around about 2017, the price dropped below this $20 a megawatt hour, the price that was being bid in these auctions. And that's 2 cents a kilowatt hour, which is the normal unit for household electricity. So, that's really cheap. I pay 50 cents a kilowatt hour here in Sydney for my electricity in summer afternoons. So this 2 cents a kilowatt hour is really very cheap. So this is at the, wholesale level. It's still cheap, very cheap there. But recently, earlier this year in Saudi Arabia, there was a bid of 1 cent a kilowatt hour, less than around $10 a megawatt hour for supply of electricity. So it just sort of shows, we're reaching really low costs, and with those ongoing cost reductions that are expected, those costs will become even lower. So the International Energy Agency last year said solar is now the cheapest form of electricity in most countries, and now offers some of the lowest cost electricity ever seen. Thinking of these 1 or 2 cents a watt, 1 or 2 cents a kilowatt hour type figures that those graphs represent. So that's the first part of my talk, just general introduction. But part two, how cheap can solar become? And one way of looking at that is to look at past history. And this is just a compilation, a reference given there, of all the costs and prices of photovoltaics that have been reported over the last, how many years, 40 odd years. And you can see there's this steady downward progression. And this is, again, a semi-logarithmic graph, so straight lines represent exponential reduction in prices. So from 1980 till about 2007, the prices were reducing very steadily, given by that straight line that's fitted to the data there, by about 7% a year. So at 7% a year, it takes about 10 years for prices to reduce by a factor of 2. But more recently, we've hit this more accelerated regions where prices are reducing by about 20% a year. So it only takes 2 or 3 years for 3 or 4 years for the price to reduce by a factor of 2. So, prices are now reducing very quickly. And, we're now about 20 cents a watt, as I previously mentioned, whereas on the old trajectory, it would have been, $1 a watt. So that recent acceleration has been quite important in getting us to these present low costs. And the gentleman shown there is responsible for that divergence you can see in the previous graph, the break from 7% to 20% a year reduction. And that's one of my former students, Dr. Zhengrong Shi, who is an Australian citizen, but he was fired with the ambition to establish manufacturing in his native country, China. And that was really ambitious at the time he decided to do that, because China had no infrastructure for manufacturing the cells. But he was determined to do it, and this was the opening of his first factory in 2002. And I got to do some of the heavy lifting, helping to cut the ribbon for the opening ceremony that you can see there. But this factory was extremely successful. Dr. Xi was able to compete with international suppliers of product. Our lab is very famous for developing high-efficiency cells, so his product was could at least match it with the international competition, and he could manufacture more cheaply. So he was quite successful. And in 2005, he floated on the New York Stock Exchange. So his company in China was a private company, and they were only allowed, the second half of the 1990s. So that sort of opened up the gates for, the growth of the industry, as we'll see. So this private company listed on the New York Stock Exchange in 2002. It was the first private company from China to do that. And the listing was a huge success. It was the biggest technology float worldwide of 2005, raising $400 million US. So Zhengrong started his initial company with 6 million. So this was a massive influx of capital into his company, which could then grow very quickly. So his success didn't go unnoticed, particularly amongst other people from our group who then worked with companies in China to follow in Zhengrong's footsteps and similarly raise capital from US exchanges. So Trina and Canadian Solar, who are two of the big suppliers these days, they were just assembling modules in China at the time, but they were able to move quickly to list on the exchanges. A year later, they did that. Again, one of my former students, this time Mohan Narayanan from India, was involved as Chief Technical Officer of Trina. And then soon after, 3 other companies floated, again with people from our group heavily involved in technical positions in those companies. And that transition really caused this second divergence. So there's this huge injection of capital to the industry, and these companies grew quickly, and the later ones were able to use all the best equipment and everything because they were cashed up from these stock exchange listings. And you had these very well-financed companies competing against each other on a market that was fairly limited. And the result was the costs had to drop very quickly. And these companies had to reduce their manufacturing costs very quickly or go out of business. So it really accelerated the development of the industry, this cash injection from US exchanges into companies that were based in China and manufacturing there. So as a result of that, China now leads the world in internationally photovoltaic manufacturing, although other countries like India, Malaysia, Vietnam and so on are now building up their manufacturing capacity. This is a graph I showed earlier, but it just shows recent average selling price reductions based on a logarithmic scale. And you can see, the steady growth through this competition between these well-financed companies, driving down the growth of driving down the cost by about 12% a year. This is from 2012 to 16. And then around there was a break point. And that was created by something a little bit different, I believe. That was the introduction of new technology. So that was the red line shown there. So initially more expensive than the old technology, but as manufacturers got more experience with it, the costs were decreasing quickly. So the incumbent technology had to decrease costs very quickly. So the introduction of the new technology onto the market sort of accelerated the rate of cost reductions and have put us in this 20% per year region that we've seen quite recently. And I'm proud to say that new technology was one that was developed in our labs in Sydney in the 1980s and 1990s and now found its way onto the market. So this is a team, 1985, this actual graph was, but this actual photo was, but this is the team that developed what's called the PERC solar cell technology, PERC. So you'll see many manufacturers now offering that because over 90% of the product made last year was made with the PERC technology. And the little drawing there just shows the diagram of the PN junction device that the PERC structure is incorporated into, a little bit fancier than the drawing I showed earlier. So an important point is, and important to the future, and particularly in terms of addressing global climate change, is will the photovoltaic costs keep decreasing? And, the graphs are suggesting they will. This just shows the uptake of the PERC technology. My little insert at the top there is hiding some of the graph, but Before 2017, the industry was dominated by a technology that was developed in the US in the 1970s, and that was very simple technology and easy to manufacture and so on. And then in 2017, there was a bit of a transition, and the industry transited to our more sophisticated PERC technology, which are the brown and yellow regions in that graph. And this year, the PERC is just about completely dominating manufacturing, as you can see there. That's also accelerated development of related technology. So the PERC technology works best if you have high quality silicon. So it's made a big push towards making very high quality silicon very cheaply. So that's one thing that we've seen over recent years. So the silicon that's used in the solar cell is grown by a technique used in microelectronics. You have this molten bath of the silicon material, and you dip a seed crystal into it because you really want the silicon to have perfect crystal structure. That keeps the photo-excited carriers I talked about earlier in their excited states for a longer period. So that gives you more time to get them out, and it results in a much better solar cell if you can have that excited state lifetime prolonged as long as possible. But what's been happening is people have been making better and better quality silicon so they can make better and better cells. The industry is so big now that you've got big companies working on these technologies. So instead of just growing, like a few years ago, just one crystal of silicon from the melt, what happens now is the melt is recharged between growth of crystals, and from one container now there's 4 or 5 crystals grown. So instead of getting 60 kilograms from one container holding the molten silicon, you're now getting about 1.5 tons from that container of similar size and cost. So that type of thing is greatly reducing the costs of photovoltaics. And you grow these big cylinders of material. You then slice the sides of those cylinders to get a squarish type cross-section to the cylindrical shape. And then you slice that sort of loaf of bread, not into slices of bread, but into silicon wafers by this sort of machine that's shown underneath me there. So the wires are guided up through the material, and they're impregnated with the diamond, so they cut the silicon away and make these very, very thin wafers. So the wafers are about 1/6 of a millimetre thick these days, so, much less than a millimetre in thickness. So very thin wafers. And down the bottom there, bottom right, you can see one of these big crystals grown. So all perfectly arranged silicon within that material. So, with the huge uptake of the amount of silicon used in photovoltaics, being able to take the costs out of those processes quite aggressively. So you might be able to read the figures on these graphs, but they're just showing since 2011, so over the last 10 years, the cost reductions that occurred in the cost of making those crystals of silicon and soaring them up. So the wafer is the red region, the soaring operation, and the crystal growth is the grey, but both have reduced to about 1/5 of their value 10 years ago, through this, largely through the increased volume and the increased sophistication of the manufacturing processes and so on. The other big thing that's happened, and this is something that the PERC has made feasible, is fabricating cells that respond to light from both directions. And you might wonder, why that's useful. The sun's up there and falling on the module. But a lot of stray light gets to the backside of a module, like light reflected from the ground and buildings behind, and even clouds that are, behind the module. You get a lot of light reflected onto the module from the rear. So by having a solar panel bifacial, and the photo at the right just shows a module from the front and the back, so they look pretty much the same from both directions. By having bifacial, you can boost the output by somewhere between about 5% if you don't do too much to increase that rear light falling on the module, to 20% if you make a bit of an effort. So a 5 to 20% boost in output, essentially for very little extra cost. So that's become quite popular now. And you can see these modules here, they're mounted on that what is a sun tracker. So the modules track the sun in its motion through the sky, and that's a very common way of mounting the modules in large fields to get the maximum power from them by pointing them as closely as possible to the sun. The other thing that's happened is the cells are getting stacked more closely within these modules, and this is a prototype for what's done now. So we supply a lot of cells for solar car racing in the 1990s. When we were making the world's most efficient cells, we could charge companies like Honda anything we wanted to get the world's best cells onto their car. But we figured that if we overlap the cells, we could get more power output, because there'd be no spaces between them and so on. And that was an approach we pioneered. Also, cutting the cells into rectangles we pioneered as well, because in the short direction of a rectangle, you don't have to carry the current as far. So that means less resistance losses in that direction. So you can decrease the resistance losses within the module by cutting the cells into half. And that's what happens now. There's other advantages that flow from that I won't have time to go into. So this, either having the cells overlapping or shingled, or other techniques have also been developed to provide alternatives that can do nearly as good by manufacturers to allow the cells to be squished up really closely. So they're now packed a lot more densely in the modules. And because the PERC has allowed you to cut the cells up quite simply, because there's patterning done on both the front and the rear surface in the cell fabrication, so it's easy to design them to be cut into half. So for a long time, a 6-inch square wafer, 156 millimeters, was the industry standard. But just over the last couple of years, with the uptake of PERC, people have realized that they can cut the PERC cells into smaller wafers quite easily. So that's encouraged the use of bigger wafers. So they're now 8-inch or even bigger, 210 millimeter square wafers are now the largest that are used by the industry. So most manufacturers are now either using 182 or 210 rather than the 156 size. So you process the wafer as a whole, and then at the end of the processing, you just cut it up into the individual cells. So you save on the processing costs by doing that. So that just gives you an idea of the relative sizes of the cells. So for a long time, the solar industry used smaller wafers than microelectronics. So this graph here, the yellow just shows just a timeline for the uptake of wafer size in microelectronics. So the industry went to 12-inch or 300 millimeter diameter wafers around the turn of this century, whereas the solar industry stayed with much smaller diameter wafers, largely due to this high current output of the cells. So handling more than 10 amps that you'd get from a cell that size produces challenges with resistive losses within the module and external to it. But now you can cut the wafers into smaller cells. You can go to bigger wafers. So now the industry is going to the biggest wafer you can cut out of a 300 millimeter diameter wafer, the biggest square wafer. And, we might even get ahead of microelectronics, in going to bigger and bigger silicon diameter crystals, because microelectronics is hampered by the processing requirements, particularly making very fine line widths on these wafers, which is not required for photovoltaics. So microelectronics had this roadmap where they would go to bigger and bigger wafers over time, but the challenges with doing that fine line width lithography on these big wafers has held back the progression to even bigger wafers. But in photovoltaics, we may be able to do that. And bigger wafers mean bigger modules. The limit on module size at the moment is just how big a module can two people carry, and that's just determined by the weight of the module. So 40 kilograms is the highest weight that's conveniently carried by two people, and that's sort of placing a limit on the module size. So, about 2 or 3 square meters gives you that sort of weight. So that's what people are sort of building around at the moment. And this is the way modules are installed. Two people generally carry it to the field, and you might be able to see a couple of shadows in the background there. Two more people then clamp it onto the support structure shown here. But my thinking is that with this interest in going to bigger modules, that why stop at 3 square meters? If you get away from manual handling of the module, you can handle something much bigger. And with different technologies, people have experimented with bigger modules in the past, and these are some 6 square meter modules that were installed about 10 years back using using automated equipment for the installation. So these modules were about 100 kilo, so too heavy for 2 people to conveniently carry, but the machine had no trouble. So that might be the way the industry goes as well. So a limit on the module size is probably how big a module can you carry around the countryside or ship overseas, and that's probably determined by the size of a 40-foot container. So 8 foot by 40 foot or 30 square meters is probably the largest module size we'll see, but maybe the industry will work towards that. So I'll talk next about longer-term cell technology. So the graph on the left just shows the progress in laboratory efficiency of silicon solar cells. So the first silicon cells were made back in the 1940s, but they weren't terribly efficient. As you can see, it wasn't until the 1950s that people learnt how to make high efficiency solar cells, and that was with the development of the semiconductor industry and transistors and integrated circuits that was triggered over that period. Most of the early records were held by groups in the US. Excuse me, I just lost my timer here. I'll get it back. Yep. But in the 1980s, our group started having some success in improving efficiency. So we're the red dots there. So we took the efficiency from about 17% up to 25%. So about a 50% improvement in a technology that already had about 40 years prior development. So we're quite proud of that effort. But there were 4 cell structures. So we got to 25% at the turn of this century, 25% efficiency. And the limit is about 29%. So that's the best you can ever do. So we're getting quite close to those limits. But since 2015, there's been 4 technologies that have now also exceeded 25%. We were the only ones for a long period, but not only is there our PERC structure, which, as I mentioned, is the industry standard, but other structures that are shown there. So some of them are quite interesting in that, the one at the bottom there is the interdigitated back contact, but it has both contacts on the rear side of the cell, so completely different structure. I won't have time to go over these, excepting mention there's a big competition between these now to see if PERC can hold its position as the dominant market leader, or will some of these other technologies knock it off its perch in the fullness of time. So the battle's on to keep improving the efficiency in production. So the best manufacturers now with the PERC are doing over 23% efficiency. But eventually, I think the industry will do something like 27% efficiency with these technologies, very close to the 29% limit. But in the longer term, there's a way of getting even further or even higher than efficiency, so higher than the 27%, which I think is the limit for a single cell. If you stack another cell on top of silicon, you can actually perform better than with a silicon cell. So a silicon cell is as I mentioned before, it's a photon converter. You get 1 photon in and ideally 1 electron out. So you're doing really well if you get 1 electron out. It's generally a fraction of an electron per instant photon. Not really, but you need more than 1 photon to get per electron out. But the voltage, as I said, is determined by the band gap, which is around about 1 electron volt. So you're stuck with voltages that are less than 1 volt. The energy gap is 1 electron volt, and the maximum voltage you can get out of a cell is less than that value expressed in volts, so 1 volt. But if you stack a cell with a higher band gap on top of silicon, it can respond to the higher energy photons in the sunlight. So it can respond to the energies, so if you stack a cell with 1.5 electron volt band gap on top of a silicon cell with just over 1 volt band gap, you can get a voltage that's closer, that's higher, say 50% higher than silicon from that cell that's stacked on top. So again, you get the photon count. The top cell, is limited by the number of photons with that type of energy that are falling on, and the silicon cell will have fewer photons on it because the top cell's stolen some of them. But because of the higher voltage at the top cell, you end up ahead. So if you do things properly, one cell stacked on silicon can increase the efficiency by about 40%, and 2 cells stacked on silicon can give you close to a 50% boost. And this is just shown in this graph here. The figures on the graph on the right just shows, 1 cell, 29% is the limit of silicon, shown in green there. If you choose a material other than silicon, 33% is the limit. If you stack 1 cell on silicon, you can go up to 42%. Stack 2 cells, you get 47.5% is the limit on performance. And if you get the same fraction of that performance output, you're looking at cells that may be over 40% efficient through this stacking arrangement. So this is clearly a good way for the industry to go. The real challenge has been to find a suitable material for stacking on top of silicon. It needs to have a higher band gap than silicon, and it needs to have all the properties, desirable properties that silicon possesses, which it's abundant. Silicon is the second most abundant element in the Earth's crust. It's non-toxic, it's stable, and it's efficient. You need an efficiency of at least 20% from these cells that you're going to stack on top of silicon. So finding materials that meet all those 4 criteria has been the problem. So I've listed a list below there of material people have shown an interest in, but none of them have 4 ticks. So perovskite is very popular, and those working on photovoltaics would be aware of the huge effort that's going in to develop perovskite solar cells. So they've given the efficiency, so a tick in the far right box, and the materials are fairly abundant that are used in them, or can be abundant that are used in them. So tick there. But they involve lead. Any perovskite that's efficient is about 30% lead. So that's not a desirable material. It would be illegal under legislation in some countries to have a solar cell based on lead without special exclusion approved. And it's not very stable. So at the moment, there's been no demonstrated modules that can survive outdoors for any appreciable length of time, unlike the silicon modules, which generally come with a 25 or 30-year warranty. And then you go through the other lists there, and so on. It makes sense to stack these cells onto silicon. You could stack them onto other materials, but because the whole industry, which had a turnover of $130 billion worth of solar systems installed last year, because of that huge industry based on silicon, it'd be easier to introduce a stack cell if it was able to be, the technology was compatible with what present manufacturers are doing. So my forecast for the future is, initially, if we can develop a suitable material for stacking onto silicon that meets all those 4 criteria, we'll first go to 1 cell on silicon, but very quickly to 2 cells onto silicon. You can keep repeating that procedure and eventually double the efficiency of a silicon cell by stacking sufficient cells on top of it. But each time you stack a cell on silicon, the number of photons it's got to work with reduces by the number, or reduces to the fraction determined by the number of cells in the stack. So the contribution of the silicon cell becomes less and less. So with 2 cells stacked on top of it, the silicon cell is only giving the third the power contribution that it would be if it was by itself. So it's becoming less important to the whole procedure. And by that stage, the materials that you're stacking on silicon would be similarly well validated as compared to what the silicon is now. So manufacturers would be starting to get a lot of confidence in them and so on. So I think after that stage, we might go to what's an all-thin film cell. So silicon is probably the only material that you could make it wafers in the wafer form, and it'd be cheap enough for that to work. But But from other materials you can prepare in the form of thin films, that you only need very thin layers of them and deposit as thin layers rather than growing these wafers. So a four cell thin film stack, I think, might be the forerunner of the final photovoltaic technology. So you can stack more than 4 cells, but the transition from silicon to these thin films, I think, will occur at that boundary. And then the industry will probably keep stacking cells because manufacturers like to show they've got an advantage over their competitors. And each time you stack a cell, you get a slight increase in efficiency once you get up to 6 type cells, and then the improvement becomes less significant. Well, just final bit of my talk, I'd just like to talk about some of the issues in a future world that is likely to be powered by solar. If we're successful in mitigating climate change, keeping global temperature rises below 2 degrees, I think we'll be looking at a future where the world is largely powered by solar. And, what other technologies are required and so on. So there's been an increasing number of studies that have come to this conclusion. So, as time goes on and more people become familiar with the really low costs that we're seeing from silicon cells now, the more and more forecasts of how we can power our future, including photovoltaics as a large component in the energy supply mix that will get us to that point. This is just a study that was done a couple of years ago, one of the pioneers in this type of analysis. But it just showing the energy mix of the future. This is the installed electricity generation capacity, which goes up quite massively for 2 reasons. One is that electrifying a lot of the energy uses that are now used, now met by burning fossil fuels, for example, like in iron and steel making and so on. They'll be replaced by electrical approaches or using gases prepared by electrical means. So we'll have a huge demand for electricity supply. So that's one reason that the electricity installed capacity is going up. The other is a lot of it's going to be renewable but energy based by wind and solar. So solar in these graphs here, this is just a timeline showing how the electricity supply capacity will go up. And the yellow, brown and yellow bits are just photovoltaics in different ways of installing them. Some with trackers I showed before, some without, some on rooftops, etc., etc. The blue is the wind generation. So solar and wind are intermittent, so even though for a given capacity you get less electricity generation. So that's the other reason the total capacity is going up quite quickly. So because much of our electricity is going to be generated by these intermittent sources, we're going to require some means of energy storage. And pumped hydro energy was developed largely for nuclear electricity because it has the opposite problem. It's cheapest when it runs flat out, and it's safest when it runs flat out. So you needed storage to accommodate the fact that we didn't want maximum electricity through the night and day, but mainly during the daytime. So these pumped hydro storages were developed for that nuclear supply. So you can have them on river like the previous slide, or you can just build purpose-built storage, just a reservoir at the base of a hill and one at the top. And one of my colleagues in Canberra has studied this quite extensively, and these are locations where you've got, looking very attractive. And of course, batteries is the other way of storing, and with the rapidly reducing costs of lithium-ion batteries becoming more and more feasible. This is a big installation going in Australia, which will be 300 megawatts. So, getting to the size of 3 of these would make one large coal or nuclear power plant. The other hope is, of course, hydrogen produced from electrolysis using some of that electricity that's generated by the solar shown in the previous slide. So the hydrogen provides seasonal storage as well as a fuel for applications where electricity isn't a suitable source of the energy. So one of those is steel making. So we've just reached a bit of a milestone in that there now is steel being made using hydrogen rather than fossil fuel in the production. And Volvo just announced a few days ago that they're going to collaborate with one of these green steel makers to build their cars from steel made using green energy sources. So I think that'll become a differentiator for automobile makers, initially just the prestige ones like Volvo, but it'll be something we see more commonly of companies advertising the greenness of their electricity source. Well, that brings me to the end of the talk. So just a few pointers from it, showing the big module there on the right, the 8 foot by 4.5 foot type modules. But solar photovoltaics is going to become insanely cheap. It was a phrase coined by one of my colleagues. So we're going to see very low costs. They're already, lowest cost in history, but for electricity generation, as the International Energy Agency indicated, but we're going to become insanely cheap. Uptake of new technology like PERC accelerates the change, so more research to get these competitive technologies up. We're going to see 10 cents a watt. So rather than 20 cents a watt now, we're going to halve that cost over the next few years, 20 to 23% modules. 1 cent a kilowatt hour electricity prices will become more common. Those bids will become more common rather than the leading bid. So solar combined with wind, which is complementary in many respects in terms of when the wind's blowing and the sun is shining, storage and hydrogen will play a major role in mitigating global warming. So thank you very much for your attention.